The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees.
Good afternoon. This is a little bit of a difficult time for a presentation for the audience. For the speaker, no problem, because it wakes me up. So thank you for this. Today I'm going to talk about an application of the use of limestone filler, and this would be not inter-ground material, what Eric was telling us, but the added material. And this is a study that was presented in one of the conferences on SCC, one of the RILEM conferences, back in 2007. So it's a little bit difficult to find that paper, but if you're interested, please contact me. I'll be happy to send you a copy of the paper. So the paper was use of manufactured calcium carbonate in SCC targeted for commercial application. And this work was conducted when I was at the University of Sherbrooke in Quebec, Canada, with Mr. Canduce, who was at the time was OMIA Canada. So it was published 2007, so it's probably about 8-9 years when the work was done. Apparently, it's still relevant, so I'm happy to present it here today. We were looking at the potential use of limestone filler as an addition or replacements in SCC mixtures. And like Eric mentioned, the motivation there is to increase the powder content. But we did not want to use a lot of powder like what they do in Belgium or in Germany or some of European countries, where they go 300 kg of cement and 300 kg of limestone filler, and then that's a very, very high powder mix, no VMAs, but very viscous. We wanted to adapt it more to what we use in North America. We used a number of different limestone fillers. Here you have the grain size distribution. This is your typical type 1 Portland cement. In Canada, we call it general use. And then you have one of the betocarbs. So they had them at different grain size distribution. We tried the 20 and the 13, and here I'm showing the 8 and the 3. And the 8 and the 3 refer to the D50. So this is a logarithmic scale, and the D50 for this one would be 3 micron, and for Portland cement, it will be on the order of 15 to 17 micron. So this one is finer than cement, and this one is a lot finer than cement. And the calcium carbonate that was used over here is almost pure calcium carbonate, 95% very pure. And it was angular because you mentioned also the morphology. It was angular and uniform in color. We're looking at different applications. I'll come to the applications. And we wanted to see if indeed the use of the limestone filler has any effect on the stability. And one good test for assessment of stability of SCC is a surface settlement test. This is about 3-foot column of concrete, 8 inches, and you put an LVDT and look at the settlement of the surface. And we see over here that for a cast-in-place SCC with a water powder ratio of 0.42, type 1 cement or a GU cement will have about 0.65, 0.7% settlement. And if you replace that by 20% or 30%, by mass with the calcium carbonate that is medium fineness, it doesn't do much. It reduces the settlement a little bit. But the magic number where we would like to get with settlement test is 0.5. And we see when you go from 8 micron D50 to 3 micron, you get a lot of reduction of settlement, and 20% was good enough in terms of settlement. And that's important because when you are designing these concretes, you want a very high stability, especially if the water binder ratio, in this case water powder ratio, is relatively high, because that will give you stability, static stability, dynamic stability, but also will allow you to reduce the dosage of viscosity modifying admixture. So you could think of that as a powder addition that could reduce some of the VMA that is incorporated in SCC mixtures. The study was continued using the calcium carbonate with the 3 micron D50, and we had 3 classes of SCC that were all air-entrained. The first one was for commercial applications. So the targeted compressive strength at 28 days was 32 MPa. The second one was the precast, pre-stressed structural applications, so for girders and beams, pre-stressed elements. And there the compressive strength at 28 days was 55 MPa, and the 18-day compressive strength after steam curing was 30 MPa. And the last application we were interested in is precast architectural applications. So the requirements on the strengths are not as high, 55 MPa. They are 35 MPa, 5,000 PSI at 28 days. And the requirement after 18 hours of steam curing is not 30 MPa, it's 15 MPa. Or if you would, it would be 20 MPa after 24 hours. And I'm sorry for the metric units, but this is American Concrete International, so get used to it. So the calcium carbonate that was used, like I said, the D50 was the 3 micron, and these are mixture proportioning. So the first one is for commercial applications. We use a type GU cement or type 1 cement, and we had replacements of 0, 10, 15, 20, what Eric was saying, 15% is very typical. Again, this is before the 1L, so we're talking about 10 years ago. And the content of cementitious materials was 425. 425 is about 720 pounds per cubic yard. And for an SCC mixture, that tends to be, I would say, moderate amount of binder, a little bit on the low side. The one that is on the high side would be this one, the precast application. And there, like Eric said, again, you need a lot of powder for reducing the viscosity, increasing the paste content, and getting good surface finish for architectural finish. So you have the water-powder ratio, and then we use polycarboxylate. We use a viscosity-enhancing admixture. The dosages were low. With the 0.42, we needed some. With the 0.35, we didn't need any. And with the 0.38, we needed a moderate dosage that was mainly added for robustness. And the slump flows were all, I would say, on the moderate side. This is 25, 26-inch slump flow, and all the mixtures were air-entrained. And the concretes were extensively tested for fresh properties, all the workability characteristics for SCC, but also using rheometers for plastic viscosity, yield stress. We even looked at the thixotropy. Mechanical properties, we looked at compressive strengths, flexural strengths, elastic modulus, drying shrinkage. After 7 days of water curing, we did the drying shrinkage. And for durability, we looked at frost durability, air void system, deicing salt scaling, and the rapid chloride ion permeability test. And again, this was before the bulk resistivity and surface resistivity. So I'm going to compare the results. It's going to be always the 3 classes of the concretes. It's going to be bar charts. With the first one, it will be the control without any calcium carbonate, and then going 10%, 15%, 20% replacement by mass of the calcium carbonate with the 3 micron D50. So this is the super demand to maintain, in this case, a slump flow of 640 or 650. You see the super demand because of the better packing density and the reduction of the Portland cement. We get very slight reduction of super plasticizer. And in the case of the much lower water to powder ratio, where you have higher amount of powder and less water, the use of calcium carbonate allowed us to reduce significantly. So here you have 12 liters per cubic meter, going to about 7, 8 liters per cubic meter after 20% replacements. So that has significant implication on strength gain, but also on cost. For the architectural application, it was a type 1 cement. You see, again, there's really hardly any difference in terms of the super demand. The cost, it's always touchy to give these, but please consider this is Canadian dollars. It's about exchange rate of 135, and these are numbers of 2007. So frankly, I don't know what the numbers are. We can take them as percentages. But the idea is that for the cast-in-place applications made with type 1 cement, whether you add limestone filler or not, you're not really getting much economy. Maybe a little bit economy in this case because you are reducing the super demand. But when you get into the precast application, because of that very, very sharp reduction in super demand, that reflects also on the cost. And I must say also here we didn't have any VMA. And again, the precast application follows very much the super demand. So what really is driving the cost over here is the super demand. If you can get something that gives you a better packing density, lower water content or super content, that would have that implication of the cost. So you can say over here, you can deduct for yourself that limestone filler that is finely ground is about the same cost as Portland cement. Yes, you're right. Not very different. As we go, it would be more cost effective. In this case, we are looking for high value added for specific applications, and that's for SCC mixed designs. We also looked at the rheological properties. So this is an example of SCC for commercial application. The slump flow is maintained, so the yield stress is the same. And then we see that the plastic viscosity with the replacement goes considerably lower, 40-50% lower. And for cast-in-place application, that has a lot of benefits for surface quality, for ease of pumping, ease of finishing, placement. So viscosity is important, but of course you have to make sure that it's not too low because that will get you in trouble in terms of stability. But the static stability in this case was very, very good. So surface settlement with the replacements of Portland cement was 10, 15, 20%. We see the settlement is improving quite a lot. So that's excellent. And that has implication on durability, on the bond with rebars. So it's not only a fresh property, it has implication on the... So this is with type 1 cement. When we have a type 3 cement, the replacements of type 3 cements with limestone filler, we see that it's increasing in settlement, which is odd because this one decreases it. But you have to think this is a type 3 cement, thixotropic. The concrete is left for hours without any shearing. So thixotropy kicks in, we are using high type 3 cement, and then we have an increase in settlement when you are reducing that type of cement. But again, the number we usually look for in specification is a maximum settlement of 0.5%, and these numbers are there. And the precast application, again, we go here to water powder ratio 0.5, replacement of type 1 cement, and again, we see the same trend as above. The finely ground filler is enhancing the stability of the concrete. Filling capacity, this is a test that was proposed to AASHTO and was adopted. It's a test that combines the filling ability, which is a slump and the V-funnel, with the passing ability, which J-ring, L-box, or others. It's a very severe test where the concrete has to flow in 2 dimensions among closely spaced rebars, about 1.9 inches, 34 millimeter, and without any consolidation. And we look at the percentage of that space that could be filled with concrete. And the number that usually we see in recommendations for highly reinforced structural sections, for example, in earthquake moment-resisting frames where you have a lot of lateral reinforcement, is 80% and above. So these concretes, these SCC, obviously are developed to be extremely workable. And we see that the limestone filler, whether you use it or not, it's not really affecting much the passing ability. It's already very good. It's not hindering it either, which is important. One thing that was very interesting is the form pressure. So when you are constructing with SCC, you cast concrete fairly fast because it's a liquid pressure. You assume it's liquid pressure. So this is a sacrificial column that we cast. It's 1 meter or 3 feet. We have some sensors. We can pick up the pressure, and this is the pressure at the very bottom. See the casting rate is 30 feet per hour, so it's very, very fast. And then the initial pressure that is exerted is 80% of the equivalent hydrostatic pressure. So this would be 25 kilopascal. This is 20 kilopascal pressure. And we see whether you are using a type 1 cement or calcium carbonate. Initially, nothing changes. It's the same rate of decay of pressure. But with the calcium carbonate, we get a much faster decay in pressure. And that's very important. So that's the first indication that tells us that this limestone that is very fine is doing something to the hydration of the cement in the dormant period. And what we think is happening is that you get an acceleration of the hydration of C3S. Eric mentioned that you get nucleation, pumping of the silicate because of the high calcium. But also you get an initial reaction between the calcium carbonate and the aluminum phase, the C3A especially, to form some calcium aluminate monocarbonate. And this is something that has been documented in the literature that can explain some of the early strength development when you are using calcium carbonate, especially finely ground calcium carbonate. So this is an interesting surprise. You came across it by accident, but you can definitely take advantage of this property. We also looked at the heat of hydration, and this is semi-adiabatic using a 6x12 cylinder that is insulated in styrofoam box, about 3 foot cube, and you are looking at the cylinder over here in the styrofoam cube, and you're looking at the semi-adiabatic heat rise, and the second one from the right is the type 1 cement or the GU, and you see with the type 10 you have a little bit of a shift, a little bit of a delay in terms of the dormant period, but with the 15% and the 30%, the dormant period gets shorter, so the end of the dormant period is shorter, and then initial setting and the final setting would be also faster than the type GU cement. So 15-20% is enhancing the early properties, the heat of hydration, and development of the microstructure. And the same thing was noticed when we do steam curing, and the steam curing in this case for the precast SCC, both precast for architectural applications, but also for structural applications. And you see over here that the heat of hydration of the type GU cement is here, and 10% is the blue one, and the green one and the brown one would be 15 and 20%, where we see similar behavior as for the cast-in-place concrete. So again, different cements, different water binder ratios, different admixture dosages, but the calcium carbonate signature, if you would, is similar. I'm showing here the compressive strengths, most curing until 28 days, and this is for the cast-in-place SCC, was water to powder ratio 0.42, using type 1 cement or GU cement, and then 10, 15, 20%. And as expected, later age strengths are hindered a little bit by the use of the limestone filler. And in this case, the target was getting 32 MPa at 28 days. And again, was mixed design. If you know this, you can anticipate it and compensate for it. For the pre-stressed application, we had a pre-stressing chamber. So this is the regime that you use for steam curing chamber. And these are the temperatures inside cylinders. Again, you follow the same regime. And then in terms of compressive strengths development, this is for the compressive strengths at 18 hours, at the end of 18 hours of steam curing, well, 16 hours plus 2 hours of cooling. And this is for the precast SCC. So for the precast pre-stressed, we had 30 MPa, 18-hour strengths. You see that you get it, and then once you get to 20%, you don't have it anymore. And this is a type 3 cement. And for the type 1 cement, it seems like you are promoting strength gain because of nucleation when you are replacing type 1 cement with calcium carbonate. Again, the targeted strength at 18 hours of steam curing was 15, and you'll largely meet that requirement. And after 28 days, the structural pre-stressed concrete, we had a 50 MPa requirement. And again, we meet it everywhere except the 20% calcium carbonate. And the 35 MPa requirement was met with all 4 concretes, with or without calcium carbonate. So the document 212 proportioning mentions something about shrinkage. This is what we had in terms of shrinkage. And these are drying shrinkage values after 7 days of moist curing. We see here after about 120 days of drying, followed with 7 days of moist curing, the type GU cement has the highest shrinkage, about 700 microstrain, and the use of finely ground limestone filler is reducing, especially in the case of 10%, and then a little bit less with the other 2. We also looked at autogenous shrinkage and creep, but I'm not mentioning that here. They are in the paper. So in terms of freezing and thawing, here we have some interesting results. These are all air entrained. 6 to 9% air entrainment. And we looked at the spacing factor. Spacing factor is between 190 and 270 micron. The Canadian standard calls for 230 less, so 0.008 inches. So they go a little bit higher. But despite of that, regardless of the concrete mixture, all of them met the requirements of having at least 80% durability factor after 300 cycles of freezing and thawing. So the cast in place was the 0.42, the precast was a 0.35, and the precast architecture was a 0.38. All of them had excellent pre-sow durability. The surprise was in terms of de-icing salt scaling. And de-icing salt scaling, we do this ASTM 672. So the samples are subjected to 50 cycles of freezing and thawing. And then you see over here that the Canadian standards calls for a maximum scaling materials of 500 grams. Some standards go all the way to 1,000 grams. So 500 grams, we see that the concrete without any limestone meets it very well. With 10%, it meets it very well. But beyond 10%, we see that we have high numbers of scaling, despite the fact that the spacing factor was high, it was acceptable. And again, this goes because we have water powder ratio or water cement ratio, effective cement ratio, that gets to be pretty high to ensure good free-sow durability. But when the water cement ratio is lower or the water powder ratio is lower, regardless of the limestone powder, we are well below the 500 gram per square meter limit. So we are at 150, which is excellent scaling resistance, and the same thing for the precast pre-stress applications. In conclusion, if you were to replace 10 to 15% of the cement with finely ground limestone filler, and this is again D50 of 3 micron, it increases the packing density, which has significant effect in static stability. Cast for all kind of concretes we tested, and then it also reduces viscosity, it reduces the cost, but the cost is very proportional to the reduction of super demand. In terms of mechanical properties, we noticed that the acceleration of the early hydration of cement, and you notice this by the faster constellation of form pressure, but also the shorter dormant period for the tested concretes, limited loss in the one-day strengths, and limited loss at the 18 hours after steam curing. In terms of durability, despite of the very good air void distribution, we got excellent freeze-thaw durability, but we were not recommend for this type of calcium carbonate to go above 10% when we are using it for pavements or for sidewalks when the water to powder ratio is on the order of 0.42. So if we leave it to 10%, we don't think there's a problem. If your water powder ratio goes lower than that, or your cement is a type 3, then again, we don't see any problem with scaling resistance. So if you would like to know more about this, because we have a conference in Washington, D.C. in 2016, we're expecting about 200 papers on SCC. If you'd like to learn more about it, please join us in Washington next year. Thank you.